good noon. It's just noon. It's not morning. It's not afternoon. I guess it's 1 minute afternoon, technically. All right. Happy Monday. Let's do some review. It feels like a long time since we last met. So, and it kind of was Wednesday. Yikes. We introduced compound interest, right? So compound interest is when you've deposited some amount for into a savings account, and then at some frequency, they calculate the amount of interest that you've earned and it gets added to the principal amount, right? And so that means that you're earning interest for the next period of time, right? So some generic period of time. You'll earn interest on not just your principal, but also the interest that you've already earned, right? So that's kind of fun. And so compound interest, not as fun if you've borrowed money, right? It's fun if you've saved money, but it works in either case. So compound interest is when the amount of interest earned is added to the principal amount, okay? So when the amount of interest earned is added to the principal amount at some frequency. Let's see here. Mute everyone. There. It's supposed to mute. I don't know. Whenever I'm in an online meeting and I'm not supposed to be on mute, I'm constantly checking it to make sure that I actually am on mute. I don't know. There's something kind of, even if I'm not saying anything, there's something terrifying about it. So with compound interest, right, we introduced a set of new formulas, or new to us, here. So we're in the compound interest section now. Notice that we're just working our way through the formula sheet, right? And so we will introduce these two formulas, these two final formulas for compound interest. Today or Wednesday, we'll see kind of how we're doing. Let's see here. But last day we did introduce these formulas, right? The main one being the first one, right? All the other ones, you can rearrange the first one to get, you can solve for PV, which is the present value. You can solve for I and you can solve for N, right? A little bit more complicated, but that's why they're on your formula sheet so that you don't have to derive them necessarily, right? And we did practice problems solving with each of these, right? But this one is your main one. And also these guys we used a lot, right? So let's just quickly outline what each of these items are. Okay, so where the future value, FV, is the future value. And PV is the present value. In terms of a timeline, right, it will always be that PV comes before future value, right? So you can solve from the PV to the future value, or you can take the future value and solve it back for PV, right? But you have to have one of those two in order to solve for the other one, right? And so on a timeline, PV is always on the left and FV is always on the right. Which means what? Which means that the present value has to be less than the future value, right? In terms of an investment, you take $100 and you come back a year later, what do you expect? You expect it to be more than $100, right? Not less, right? Because you have invested it and you're earning interest on it, right? Same thing, you borrow $100. If you pay it back a year later, you can't just pay back $100. You have to pay back $100 plus interest, right? So it's going to be more. And so here, right, the present value will always be less than the future value. Okay. Doesn't matter how you roll it, right? You've invested or you've borrowed, either way, the end amount is always higher. Okay. Sometimes it's good and sometimes it's bad. So moving through this formula, right, we've talked about FV, PV. In terms of linking it back to simple interest, right, we used P before for simple interest, and then for some reason it switches to PV. So that's the only change. Nothing conceptually has changed. It's just notation. Our next variable is going to be I, but notice I is also on this formula sheet, right? And so I, lowercase I, is the periodic interest rate. Where I, right, I is R over F. Okay. R, we remember, is the nominal rate or the annual interest rate. Okay. So where R is the nominal rate, nominal / annual rate, and F is what? The compounding frequency. Remember, we said, okay, for compound interest now, I'm going to have some principal value, and then I'm going to, at some frequency, calculate how much interest I've earned, right? And that frequency is F. Okay, and so this is the compounding frequency. And I think I have room to spell it out here, frequency. Okay. So before, in simple interest, all we needed was R, right? But now we need that R and F, and then we can calculate I. Okay. So it's just that extra little step that we need in order to use this formula. Finally, we need N, which is the number of compoundings in the term. Okay. So N is the number of compoundings in the term. Now notice, N is also on the formula sheet. It's time, T is in years still, right? So that hasn't changed, times the frequency, which is the compounding frequency, right? Which makes sense. If I tell you that we're compounding 3 times per year, right? And I've invested for 2 years. How many compoundings do I have? I have 2 times 3, 6 compoundings, right? So nothing really that crazy here. So N is T times F, where T is time in years. And I'm not going to do F because we just did F, right? That F is the same. Okay. But I'm going to end it here because I've got a page break. I don't want to go over that because I think that's plenty for a review. We're going to use it all again today, so I'm not too worried about that. Okay. But what we said was for compound interest problems, we have this additional step that we need to calculate I and calculate N, right? And so this means to solve compound interest, which I'm going to abbreviate CI, compound, which I'll clarify here, compound interest problems, we need to first find I and N. So it's that additional step before we can go ahead and actually solve the problem. Okay. So this is where we usually introduce doubling time. It's just kind of a neat trick. Doesn't really have anything to do with compound interest necessarily, but it's just kind of a fun trick to know. Okay, and so and maybe I'll say not that I will, but this is section. Let's see, what section was that? 5.3 continued. Because we just didn't quite have time to finish section 5.3. All we needed to talk about is doubling time, which is also known as the rule of 72, which you might have heard about in your other business courses, just because it is such a handy tool to know and be able to use. Okay, and so the doubling time refers to how long. Oh, I'm sorry. Can you send that in an email instead? Because that's going to be hard to do. So I'll come back to, there's a, okay, nice. Did you send it earlier or just now? Okay, like I didn't see it. Okay, good. So if there's time at the end, then I'll go through it, but yeah, it's a little hard to do now. Okay, but I will. All right, so doubling time. Doubling time refers to how long an investment is going to take to double. Okay, so what we want to know is, and here's, I'm going to emphasize approximately how long will it take for an investment to double? Right. So for example, if I have $100, how long is it going to take to have $200? Right. $10,000. If I double it, I have $20,000. Right. So $10,000. How long is it going to take to double to get to $20,000? What's kind of fun about the rule of 72 is it doesn't matter what the principal amount is, right? So here we have these present values and the future value, right? But in general, we have x going to 2x, right? Okay. The cool part about the rule of 72 is, like I was saying, it doesn't matter what the principal value is, right? It's the doubling time, you calculate it the same way. So I'll say a cool feature of the rule of 72 is that it doesn't matter what the present value is that it doesn't matter what the present value is, the doubling time applies to all present values, right? That could be $1 growing to $2, right? So the rule of 72 is what? The rule of 72 says that the doubling time in years is approximately 72 divided by the percent annual rate. This is the only time where we actually use it as the percentage. Okay. So here, note this is the only time we do not convert the percentage to a decimal. We do not convert the percentage to a decimal. Okay. So what happens is we have approximately 72 times R times 100%. Right, so R is that decimal, but then you have to multiply it by 100. Usually that's how it's given in the question, so it's not too bad. Okay, but let's see here. All right, let's do an example. Example 183. Copy. Okay. An investment of $5,000 is going to be left in an account that pays a return of 6.75% per year, compounded annually. So the rule of 72 doesn't really care about compoundings or anything like that. Okay, and so it's just an approximation until it reaches a future value of $20,000. Okay, use the rule of 72 to determine roughly how long this will take. Okay. So what has to happen here in terms of we can draw it out and we can say, okay, well, I need 5,000 to grow to 20,000. Yeah. It tells me to use the rule of 72. So then I'm going to be talking about doubling time. Okay, and so if I double 5,000, I get what? I get 10,000. Right? So here, this is going to take one doubling time. Whatever that doubling time is. And then 10,000 has to grow to 20,000. Luckily, of course, it is just a double, right? 10,000 times 2. So again, this is one doubling time. So in terms of time, right, I can use the rule of 72, which says that each doubling time at 6.75% is 72 divided by 6.75. Okay. And so here, let's see here. 100% is 6.75%. Okay. So we have the doubling time is approximately 72 divided by 6.75, which is approximately 21.33 repeating years, or 21 1/3 of a year. I'm not going to worry too much about it. right? I'll just use the decimal. Oh, no, should I use the calculator? I see now that I skipped a step here, 10.66 repeating years, which means that this stretch of time is 10.66 repeating, or let's call it 10.67 years, right? And so here, because this is an approximation to start with, so I'm not going to be super crazy about keeping all the decimal places in this case. Okay. And so this chunk of time then is roughly 10.67 years. And this chunk of time then is also roughly 10.67 years. Because remember, it doesn't matter what the principal investment amount is, right? It's just the doubling time depends on the rate, right? And only the rate, 6.75. So then the total amount of time is going to be, therefore, it will take roughly 21.33 years. Let's drop the years to double twice. Right. Or 4 if you want, 21.34. So that's kind of a fun rule of thumb, right? Especially if you are at the bank and they're throwing interest rates around, then it's a really nice way to just be able to say, okay, well, 72 divided by whatever rate they're offering me, and then you can decide if that's a reasonable doubling time or not, right? And so if it's going to take you 120 years to double your money, right, maybe that's good, maybe that's bad, it depends on the situation, but it's kind of just a fun trick to have up your sleeve. Okay, so that goes there. This, all these papers everywhere. Oh, I have a note here. It's from last time I taught this, but the final exam schedule is posted. Our final exam is online, right? But it is, I want to say one on April 21st. Let's see here. And I'm going to add that to the top just in case. So just a note. The final exam schedule is posted and it is April 21st from 1 to 4, and it's online. But you are going to have to write in that time. Okay. So feels like it's a ways off still, but it'll be here before we know it. And so that's a Friday, but then when it's over, it'll be over, I guess. Okay, good. All right. So section 5.4 is just kind of a section where we tie it all together. We don't really learn anything new. It's just applying these formulas that we've learned in kind of a bigger problem. Okay, and so let's see here. There. It's called the same thing as in chapter 4, I think, equivalent payments and payment streams. Right. So equivalent payments are those scenarios where Bob has borrowed money from Joe, and the original agreement was that he was going to pay it back in 3 years and in 5 years, but now he's come into some money and he's going to pay it back early. How much should he pay him for it to match the original value that he was supposed to repay? Right. And so we'll start it off with a bang. We'll start with an example. Okay, so we're going to do example 185. A little bit of dirt there. Okay, so it's kind of a big one. That's why I post them in advance, but here we go. So what I want to do is just focus on picking this apart and just identifying what we know and then putting it on a timeline, of course, because that's what's going to help us out. And then eventually we'll be able to solve this problem. Okay. Doug's original intention was to settle a financial obligation with 2 payments. Okay, the first payment of $1,500 was due 1 year ago. Okay, and the second payment of $2,500 is due 3 years from now. So first, I'm just going to read it out and just kind of get the lay of the land. Okay, Doug missed the first payment and now proposes 3 payments that will be economically equivalent to the 2 originally scheduled payments. There's a rogue equivalent in there I scratched out. The replacement payments are $1,000 today, a second payment in 1.5 years, okay, and a third payment twice as large as the second in 3 years. Oh boy. What should the second and third payments be if money can earn 8% compounded semi-annually? Okay. So what I want to start with here is, okay, first just establish I only have one interest rate. So I'm just going to deal with that right away. Okay. And 8%, so R is 0.08. And it's compounded semi-annually. Let's use a different color here. There. Which means that F is 2, right? Compounding twice per year semi-annually. Remember we made that long list of compounding frequencies and what the F is, right? What the F? Right, and so just remember to have that handy somewhere. The trickiest one is biweekly, which F is 26, and quarterly, where F is 4. And those I think are the only hard ones. But semi-annually, F is 2. So one thing that I can deal with right away is I can find I, right? I can find the periodic interest rate. Okay. So here, I'm going to say that I is R over F, which is 0.08 divided by 2, which is 0.04. Good. Something is finished. Okay. So that feels good. Okay. All right. So next thing I'm going to do is probably map out the original repayment scheme. Okay, so because there's going to be an original repayment plan and then the new repayment plan. Yeah. So I'm going to start with the original repayment schedule. Doug's original intention was to settle a financial obligation with 2 payments. The first payment of $1,500 was due 1 year ago. Okay, which means that I'm going to have today as a reference point, right? Because it's 1 year ago, and then a second payment due 3 years from now. Okay, and so that's what I need to figure out first. Okay? And so I'm looking at a timeline that looks like this. Okay, so here I am today, 1 year ago, and 3 years from today. I have amounts, right? What was due? So 1,500 was due 1 year ago. He didn't pay it though, so now he's paying interest on that. Doug. Doug just retired last year, I guess, but he was in the department, and he's a funny guy. So, and I'm assuming it's from him, but anyways, what was due 3 years from now? 2,500. So whatever he repays has to be equal to these amounts with time incorporated. Okay. So now it says, okay, Doug missed the first payment. So this payment he missed, okay, and now proposes, so today he proposes 3 payments that will be economically equivalent to the 2 originally scheduled payments. Okay, and so let's now map out the new repayment schedule. One thing that I'm going to do is I'm going to keep the same timeline, copy. Wait. Because they have to match. Okay. So I use that same original timeline because otherwise it's going to be hard to visualize. Okay. But I don't keep the dollar amounts quite yet. Okay. So the replacement payments are $1,000 today. Okay. A second payment in 1.5 years, and a third payment twice as large as the second in 3 years. Okay, so the replacement payments are, and let's maybe use, I'll use green here, $1,000 today. Another payment at 1.5 years from today. Notice that the second payment is just an amount that we need to solve for, right? And so what's the trick here? The second payment, a second payment in 1.5 years, I am just going to use X, right? It's the same trick that we learned in terms of its simple interest, but then I said, well, we can use this for compound interest later too. And here we are. Okay. So we're going to try to solve for X. Okay. So then, and a third payment, which is twice as large as the second in 3 years. Now, how am I going to denote that? Well, it's twice as large, so 2 times X. Okay. Okay. What should the second and third payments be if money can earn 8% compounded semi-annually? All right, so what we need to do first is we need to pick a date where we can draw all this money to, okay? And it doesn't actually matter which date. Okay? You'll find that X works out to be the same, although there is kind of a trick to it. If you're solving for X, then the easiest thing to do usually is to just draw all your money to this X, right? And then, because then you don't have to discount it or move it, right? All these other dollar amounts, right? We're going to have to move using these arrows, okay? And so what I'm going to do here, what I suggest is use 1.5 years as the focal date because it makes it easier to solve for X. Because it makes it easier to solve for X. But it doesn't actually matter which date you draw them all to, as long as you make all the payments equivalent to each other. But it doesn't matter which date you use. I just like to draw it to X because otherwise I have to move X around, and that's annoying. Okay, so what we're saying then is, okay, all these payments, so this original repayment schedule has to be worth the same as this new repayment schedule. So what we need to do is we need to figure out, well, what is the value of $1,500 due 1 year ago? How much does he need to pay back at the 1.5 year mark in order to make that equivalent, right? And how much does 2,500 due in 3 years from now, but paid back in 1.5 years earlier, right? Then what's the equivalent payment to that? Okay. So what we're going to have is, I can now combine this into one timeline. Okay. So I like to map it out like this as 2 separate timelines. And sometimes I'll just use 2 separate timelines, but just to draw it all together, I'm going to put them on the same timeline. Okay, so you can work with 2 different timelines if you prefer, but now we can draw these payments on one timeline. Okay. Carefully using subscripts to denote the order of your calculations. Carefully use subscripts to denote the order of your the order of your calculations. Okay. So again, I'm going to have this original timeline. Okay. There. Okay. I'm going to add the 1.5 year mark. I'm going to use light blue for the original payments and green for the new payments. Okay. So I owed 1,500 and 2,500. And then I'm going to pay $1,000 today and X. Oh, sorry. I'm going to put this one line down there. And 2X. Okay. So using this again as our focal date means that we're going to draw all these arrows to the 1.5 year mark. Okay. And so here, and I guess I could have given myself more space, but oh well. This 1,500 has to be turned into some future value 1. Okay. Notice I'm pulling 1,500, I'm pulling it forward. So at the end of that is a future value. Okay. Now the 2,500, that's the second thing that I'm going to calculate, right? And so now I'm going to pull it backwards to the 1.5 year mark. And so that looks like this, which means if I'm pulling it backwards, it becomes a present value. Present value 2. That has to be equal to, so these two added up has to be equal to x plus what? Plus 1,000 pulled forward, so borrowed for another 1.5 years, so a little bit more, and 2x drawn back, so repaid early, so drawn to this focal date. Okay. And so here, this becomes a future value 3, and 2x becomes a present value 4. So notice how I've shown the order that I'm going to calculate these things, and let me just clean that up here. There. Okay. I'm going to do a future value, present value, future value, present value. Fine. Okay. And then I'll be close to being able to solve for this x. Okay. So therefore, in order for these payment plans to be equivalent, what we've said is the future value 1 plus present value 2 has to equal x. Don't forget about that x, right? That's the amount that we're solving for, and it is some amount, right? And we just don't know what it is. X plus future value 3 plus present value 4. So we know that these two things have to be the same. What's our kind of logic here? We're able to solve for these two. We have these values, right? So we know what x plus the future value of 3 plus the present value of 4 have to equal, right? And then we'll be able to use that to solve for x. Okay. So there's only one variable. Okay. So let's see here. Let's do a little bit of work on the, we found I. I'm just going to bring that down here. So I copy. Just going to put it down here, and I'm going to paste it and maybe make it a different color. Style. What color haven't I used? Green. No, I have used green. Oh boy, here, there. How's that? Remember, for compound interest, we need to find the number of compoundings for each of the arrows, right? And so here, let's see. N is time times the frequency. Now, time is in years, right? And so 1 year ago today, from today, or 1 year ago, all the way to 1.5 years from now, that makes 2.5 years, right? And so this is 2.5 times 2. Remember, the frequency was 2, right? Semi-annually. So I get 5 compoundings here. How many compoundings in from 1.5 years to 3 years? Well, that's 1.5 years in distance, right? And so N is 1.5 times 2, which is 3 compoundings. Same thing for this one, although it's not the same stretch, it's not the same 1.5 years, but it's the same length, right? And so N is 1.5 times 2, which is 3. Oops, 3. And finally, this is the same amount of time, right? So n equals 3 again. So really, really important that you're calculating I and finding n for all these arrows, right? Now, this is a complete timeline. Okay, so there's a huge amount of work that goes into making this timeline, but now we're just ready to use the formulas and we can just figure out all these values, right? So future value 1 is present value times 1 plus I to the power of n. Okay. If I want to solve for the future value here, I just go to the left-hand side of the arrow. That's my present value. And so I get 1500 times 1 plus 0.04 to the power of n, which is 5. I get 1,824.98. Now, I don't know if I've rounded in my notes or not, but what I'm going to do is I'm going to just write out all the calculations and then use the calculator on the screen. So I'm just going to write them all out. So that's the first thing done, right? If I fail to repay 1,500 1 year ago and I borrow it for another year and a half, right? What would I have to pay back? 1,824.98, right? Just to keep it all on the same page, I'm going to calculate present value 2 over here. The present value formula is FV over 1 plus I to the power of n. Now, if I want the present value, then the future value is what's on the right-hand side of that arrow, which means it's 2,500. Oops. 2,500 divided by 1 plus 0.04 to the power of, and I think n is 3 for all of these, right? The remainder, which is 22.49. Okay. So the value of the loan, right, at the 1.5 year mark, right, 1.5 years from today, is these two added up. Okay, so what I'm going to do is I'm going to bring in the calculator and just confirm these values. Oh, that's not the calculator. That's the graphing part of the calculator. All right, here we go. Let me grab those values. All right, so I had 1,500 times, you don't need the multiplier because it knows the bracket is multiplying, but just in case, 1 plus 0.04 to the power of 5. Okay, so it was rounded. And you know what I'm going to do? I'm going to move this up. And I'm going to call this F. What can I call it? F1 equals, so future value 1, because then I can refer to it, right? So then if I do F1 again, it knows what that value is, right? So I'm going to use these variables because then I can plug them in easily, right? And so P2 is equal to, is equal to 2,500 divided by 1 plus 0.04 to the power of 3. So then F1 plus P2, that's the value of the original loan 1.5 years from today. So I'm going to bring this in. So therefore, the value of the original repayment scheme or schedule, I'll say scheme just to introduce a new term that means the same thing. The repayment scheme is future value 1 plus present value 2, which is 4,047.47, right? Which is from here. So what does that mean? That means that the value of X plus future value 3 plus present value 4 has to add up to 4,047.47. Yeah. So which means X plus future value 3 plus present value 4 must equal 40,047.47. Otherwise, they're not equivalent to repayment schemes, right? And so that may sound obvious now, right? But just keep that in mind when you're working through your own problems. Okay, so X is what I'm solving for, but I'm not quite there yet. I can solve for future value 3 and present value 4, sort of. So let's go ahead and do that. Future value 3 is the present value times 1 plus I to the power of n, which is, in this case, we have a dollar amount. It's $1,000, has to get pulled forward for 3 compoundings. So 1,000, 1 plus 0.04 to the power of 3. So one easy change that we could make is, what if the new repayment scheme has a different interest rate, right? Then you would need to keep track of that here. But in our case, it's the same across the board, so we won't worry too much about it. I have 1124.86. Now the present value 4 is the future value divided by 1 plus I to the power of n, but the future value is just 2x. We know how to deal with this, right? But it was last week, so we'll just take it a little bit slow. But 2x has to get pulled back to some principal, some present value. So the future value is 2x divided by 1 plus 0.04 to the power of 3. Right? Okay. I can rewrite this, right? 2x. I can pull this x outside and still multiply it, right? And so what does this turn into? This becomes 2 divided by 1 plus 0.04 to the power of 3 times x, right? That's the same thing. So what do I need to do? I need to find this value, right? This coefficient of x, which is 77993 times x. Now I'm going to confirm that with the calculator here. Let's see if I can do it side by side. Okay. So F3 is equal to, right, using that same notation, just in case I want to. So this is the equivalent of storing things on your calculator, right? And so then I have 1000 times 1 plus 0.04 bracket to the power of 3. 1124.86. Good. Then I need 2 divided by bracket 1.0. I guess I shouldn't skip a step, although it's fine, right? 1 plus 0.04 is 1.04. Safe, but not what I've been doing. Okay. So this, I'm going to call this the coefficient of x. Okay, or maybe I'll call this, I'll just call it P4, why not? P4 equals. Yeah. So mine's just a little bit rounded, but that's okay. All right. I'm going to screenshot this. Done. And close this out. Paste it in. Just like that. Okay. Good. So we're getting there. We're getting there. So what did we say? We said that, okay, future value 1 plus present value 2 has to equal, right? And that's important. It's the whole problem. Has to equal x plus future value 3 plus present value 4. We already solved for this first one here, right? And I can do it, I guess, again. 182498 plus 222249 has to equal x, which we don't know what it is yet. That's what we're solving for, plus the future value 3, which is 1124.86, plus present value 4, which is 1.777993x. Okay. I'm actually going to keep all these here. But I guess not in my written work. Kind of confusing, I guess. All right. 177992717 times x. Notice that the only variable that I have here now is x, right? And we know how to solve for x in this case, right? We've already said that, okay, this side is 4047.47, I think. Yep. Has to be equal to x. So this is 1x, right? So notice you don't want to forget this 1 times x, right? Because then when you pull out the common factor of x, you get 1, right? You have 1x plus 1.77x. right? So now you have, I'll write you have 1 plus 1.77799217 times x plus 1124.86. Okay. So this becomes, so 40, 47, 47 is going to be 2.77799217x plus 1124.86. Solving for x, right? You can subtract 1124.86 from both sides and then divide both sides by 2.77, blah, 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 blah. And then you get, so 40, 47, 47 minus, and maybe I'll bump this over here. 47 minus 1124.86 is 2.77799217x, which means that x is going to be 4,047.47 minus 24.86 divided by 2.7779921717. And this is where I'll bring in the calculator. Okay, here we go. Oops. Try to do it on the side here. All right. So, oh, it's showing up a little bit weird, but in the past, it's sorted itself out. Talking about what's going on over here, I don't know. All right. So I wanted first to do F1 plus P2 is going to be the original. So O equals that. Okay. My new one, N, equals where is it? F3 it's my first time using variables so extensively in Desmos, but I think it's pretty clever, but I am finding I'm a little bit slow, but that's okay. And then times 1 plus P4 and times X. Now it doesn't seem to like that. That's okay. Oops. So what I'm going to do is I'm going to take the original, I'm just going to do the math here, minus F3 and throw brackets around that because then I need to divide it by P4 there. That is 1 plus P4 there. That's what I'm going to bring in. So then X, oops, X is 1,052 and 6 pennies from here. we can easily find 2x, right? So, and 2x, and I like to put a little flair on my x's, is 2 times 1052.06, which is 2 times that answer, 2104.11. So that means that this amount is what they would need to pay. So, or Doug, I guess he would need to pay 1.5 years from now, and 2104.11 3 years from now, in order for those all to be equivalent. Oof. This is one of the bigger types of questions that you're going to need to tackle, right? And it always follows this format, right? Oh, Doug borrowed money. Now he can't pay it. So he's proposing this new repayment schedule. And what should these payments be, right? And so you'll see more for practice. And then it'll be on test 2, which is sort of coming up. When is test 2? It might be next week. I think so. All right, I'll check, but I think it might be next week. Okay. Because we're working through. Yeah, right, it's on Monday. But don't worry. I've got a practice test for you guys to set you up. So don't worry. Okay. What I want to do is, now that you know kind of all the work and know how to use the formulas, I want to use the calculator. So now we're going to use the financial calculator to find things like the present value and the future value and all that kind of fun stuff. So section 5.5, I'll put on a new page here, is using your calculator for compound interest problems. It's not a huge time saver for these problems, but it will be for chapter 6 and onwards. And so we're just using this to get used to using the calculator. I probably wouldn't use the calculator for this, but we need to introduce it, and it's a nice introduction. So for compound interest problems. Problems. Okay. So what I'm going to do is I'm going to tilt my screen because otherwise it doesn't like it. And hey, it didn't even give me an ad. All right. So here, this is the reason why we have this calculator, right? Or you don't necessarily have a hard copy, I was going to say. So this is what it looks like in real life. Overall, not a great calculator, but it has these fun functions, these business functions, which make it worthwhile. But this is the free app, so that's what I'm going to be using, because then I can show you. The buttons that we're using are these kind of gray buttons. Now, I don't have a pointer on here, but these gray buttons, NI per Y, which is the interest per year, PV, PMT, which is going to come up in chapter 6, and the future value. So I'm going to take a screenshot here so that we can just mark it up. Oh, Fleming. Okay. There. So these values are the ones that we need. Oh, maybe because I also want to be able to take a screenshot there of the buttons individually. So there are a couple of buttons that we need in particular here. So for compound interest, we're going to need to fill in some buttons. So if you're using your calculator, all you really need to show in your work, right, is what you entered into the buttons. Okay. And so to use the calculator, or to have the calculator calculate, that sounds weird. Calculator calculate. Usually we use it for present values or future values. So calculate PVs or FVs. Okay. We need to fill in the following buttons. Okay. The first one is N. Okay. N is going to be the number of compoundings. So notice how you'll still need to find, we've been using lowercase n, but on your calculator, it's capital N, that's fine. You still have to calculate n, the number of compoundings, right? So nothing crazy there. You're going to need the interest per year. So this is the interest per year. And for the calculator, we have to enter it as a percentage. So 7%, you would enter 7, not 0.07. Okay. So this is the interest rate per year. R as a percentage, right? So what this means is, so for example, for 7%, enter 7, not 0.07. Yeah, it's just something to remember. The next thing is the present value. All these things sound familiar, right? The present value is just the present value. And maybe I'll do them all in a row here. The PMT is the payment amount. Now, this does not apply until chapter 6. Okay, so until chapter 6, you're just going to put 0 in there. Okay, or ignore it. So this is the payment amount. Not used until chapter 6. Okay. Enter 0 or ignore for now. I'm mentioning it because we will be using it, but just ignore it for now. And then the future value. This is the future value. Okay. We're also going to enter the number of payments per year and the number of compoundings per year. Now, the payments per year attached to the PMTs. And so for now, we're just going to set them to be equal to the compoundings per year. Okay. And so let's see here. To get there, you're going to use second, copy. So in the second menu, and maybe I'll paste that in here. Menu, you're going to set the payments per year. Copy. So this here, the payments per year. Where the payments per year is the number of payments per year this goes with PMT, and so goes with the PMT button, which we're not using yet, which we use in chapter 6. Oops. For now, you're just going to match it to F, the compoundings per year. For now, let the payments per year equal F, right? Same as the compoundings per year, which is the next thing. So if you use the scroll down button, copy, scroll down, then you're going to get to the compoundings per year, which is the number of compoundings per year. So let's see what that looks like. Whoops, wrong calculator here. I'm going to tilt it so it's proper. So to get to the compoundings per year, which is the last step, okay, you're going to hit second to go into the payments per year menu. Now notice it says second in the top left-hand corner. That tells you that you're in the second menu options. So then if you hit payments per year, it'll be defaulting to 1. That's fine. And then if you scroll down, you get the compoundings per year, payments per year, compoundings per year, payments per year. Now to change the payments, or sorry, the compoundings per year, you're going to hit 2, for example, if it's compounding semi-annually. But notice that the equal sign went away. So to store it again, we've seen this before, you have to hit enter. Okay. So in general, to fill in all these slots, so these are all the buttons, and we need to, or I think of them as slots, right? I need to fill in values in these slots. And so now I want to talk about how do we fill in these values. Then if I scroll up, I can change the payments per year as well. To get out of the second menu, you go second quit, which is the top left-hand button, and then you're out. Okay. So let's jot that down. So to fill in values in the calculator, we have the value that we want on the screen, and then you punch the button that you want to put it into. Okay, and so what does this look like? So there's going to be kind of two sets of instructions in the main menu. Enter the value you want on the screen. Then press the button where you want to put that value into. Then press the button where you want that value to go. So for example, if n is 3, then what you're going to do is you're going to say, you're going to hit 3. And then into n. And I don't think I have to hit enter, but I'm just going to check. It's been a while. So if I want n to be 3, 3n. So now it says n equals 3. Now, what's tricky is you can just, so you don't have to clear these values, although you can, but I'm not going to. I never do. I just always re-enter my values, right? But it'll stay 3 until you change it. Okay, so now n is 3 until I change it, which is also causes some trouble sometimes, right? Okay, so let's see here. Okay. So that's how I do it for the main menu. So in the second menu, you scroll to the value you want to change. So for example, payments per year or the compoundings per year, right? I would scroll to the compoundings per year. And then I'm going to say, okay, enter 2. Let's see here. For example, if it's semi-annually, so if f is equal to 2, then you're going to hit 2, enter, right? Enter is to set it. We need to set the value. When you hit set, an equal sign should appear. An equal sign should appear. And that's how you know that you've set it. And then to get out of the second menu, oops. To leave the second menu, oops, menu. Then you're gonna go, second, copy, paste, oof. Wait. Right. This is equal to F for now. And so whatever F is, you put it in both of those slots for now. Okay, that will change, but not until chapter 6. Okay. Just like when we're doing these problems just mathematically, right? We can only have one unknown really, right? And so all the other values have to be entered, and then you can go back and compute the value that you want. Now, usually what I do just to play it safe is the value that I want to solve for, I enter 0 initially, and then I go back and compute it. Okay, so you don't have to, but it makes it kind of nice in the beginning, at least, because we're not used to using this calculator necessarily. Okay, and so the value we want to solve for is going to be one of these buttons. So will be one of the buttons or slots, if you want to think of it that way. Enter 0 initially, and then we'll go back and compute it. Enter 0 initially. Then when all other values are entered, go back and compute, and I do mean this one, and compute the value you want. All right, and this is compute. Okay. Just one more thing. I think just one more thing. Okay. The values that we enter for the future value and the present value, they have to have opposite signs, right? And so the signs are either positive or negative, and how we're going to use the signs later is there's going to be money that leaves you and money that comes to you, right? And so although the signs don't matter now, it's good to get into the habit of saying, okay, well, if it's money that's leaving me, right? So I put it into the bank, right? Then it's leaving my hands and it's going into the bank. Doesn't matter if it's my bank account, right? So then it's leaving me, and I put it into the bank, and then I let it sit there, and then I take it out, right? And then it comes back to me as a positive amount, okay? So the values we enter for the future value, and maybe I'll do PV and FV just chronologically, must have opposite signs. So one positive, one negative. Maybe no period here. Although the sign doesn't matter now, right? As long as one is opposite of the other. Okay, so I will say, although the sign doesn't matter until chapter 6, which is really soon, right? Because we're towards the end of chapter 5 here, and so we're getting close to chapter 6. Okay, there's a test in between, but still. So although the sign doesn't matter until chapter 6, it is good to get in the habit to get in the habit of using a positive value for money coming to you. Money comes to you. And a negative value for money leaving your hands. So you are the reference point, right? If it's positive, so positive is money coming to you, right? So you borrowed money, so you received money, or you invest money, then money's leaving you and going into your bank account, right? So maybe I'll move these over and do those quick examples here. So money comes to you, you borrow money, for example, or for example, you invest money, right? That's money leaving your hands. It's still yours, but it's not in your hands. That's the hardest part, I think. Yeah. Okay. So, I don't want to scroll up to the example that we just did, but you can use your calculator to confirm those values that we found. Instead, I'm just going to start a new one. I have another example that's kind of similar. Let's see here. This is just to practice using our calculator. So $500 is invested at 7% interest per year, compounded semi-annually. What's the value of the investment after 10 years? Now, this is a simple problem, right? Especially compared to the one that we just did, right? And so, but this is just to practice using the time value money formulas of your calculator. So here we are today. We invest it for 10 years and $500 is the principal or the present value. Right? And it's going to sit there for 10 years and it's going to become some future value. Okay. And maybe I won't have, usually I don't put the present value on the timeline. So here, this is my PV is 500. My R is 0.07. The frequency compounded semi-annually, so F is 2. And what's the value of the investment after 10 years? So T equals 10. Oops, 10. I'll clean that up. And we want to find the future value. Now, what's fun about the calculator is that although we have to find N, right, it'll calculate I for us. So when using the calculator, we still need to find N, but it calculates I for us. So what I like to do is I'm just going to list the calculator entries just in a list. Okay? And for reference, I'm just going to work my way across these buttons. Okay, so they're the same ones that we had before. but I'm just going to write them out in a list. N equals I per Y equals PV equals PMT equals FV equals, and P per Y equals, and C per Y equals. So this is how we show our work when we're using the calculator. Now, the only thing I need is I need to find N is T times F, which is 10 times 2, which is 20. So that's the first thing that I'm going to enter is 20. So I said it calculates I because I need to give it the interest rate per year, which is 0.07, but really, remember the calculator needs 7. So R is 7 or 0.07, but the interest per year for the calculator is 7. The present value is 500, okay? And so to adopt that plus or the positive negative kind of convention that we established, right? So $500 is invested. So I'm taking that $500 and I'm dropping it off at the bank. So it's no longer with me, right? It's at the bank, it's mine still, right? But then after 10 years, I'm going to take it out and I'm going to take it home and I'm going to hold it, right? And so then it's back to me. So I'm going to use negative 500, or maybe I'll just highlight the negative here. Negative 500, negative, since I left it at the bank. Right, so it left my possession at the bank. Now, PMT, remember, we're not using for now. We will be using, I promise, but just let it be 0, right? So just enter 0, and then you don't have to change it until we're in chapter 6. The future value is the one that I want to solve for. So same idea as before. The one I want to solve for, I denote by an asterisk. Okay. So denote the value you want to solve for using an asterisk. Okay. Because then I'm going to fill it in and it's going to look like part of the crew, but it's not really, right? Because it's the one that I computed. Okay. Now the payments per year for now is the same as the compoundings per year. So what I'm going to do is I'm going to start at the compoundings per year, but this is how they appear in the menu. So that's the order that I'm keeping, right? It's going to be 2 because the frequency is 2 semi-annually. And then 2 to match the compoundings per year for now. Okay, so we're ready to watch the fox count. No. Oh no. Okay. Hopefully it does this. All right. So I'm just going to clear this here and start fresh. So remember, what you want to put into the slot you have to have on the screen. So 20 N. So then N equals 20. Now it's kind of confusing in the beginning because you can't really go back to it. You can't confirm that you filled it in. You can, but not in the beginning. And so now you just go ahead, right? So the next thing I want to enter is 7 for the interest per year. So notice how it's kind of scary. You just keep going. And then I want negative 500 500 negative, oops, 500 negative for the present value goes into the present value, 0 into the payment. For now, I'm going to enter 0 into the future value. You could just skip it, but I like to give you ways to play it safe. Okay, and so that's what I'm doing. The last two are in the second menu. So second, payments per year. Payments per year is 2, enter. Go down. When I change the payments per year, notice how I don't have to change it. It forces them to be the same. If I wanted them to be different, which is later on, right, then I can change the compoundings per year. But now just scroll around, make sure that they're the same, and then leave that second menu. Now we can hit compute future value, or is it future value compute? Let me just compute future value. Compute future value. Okay. Let's see here. 994.89443. Yeah. The dog just woke up and she's antsy. All right. That's it. Okay. So we can confirm this, right? If we wanted to. How could we do that? Right. So, oh yeah. To solve this, to compute the future value, you're going to hit compute future value. Okay. We can confirm this with the future value is the present value times 1 plus I to the power of n. I have all these things except for I. So the future value is $500 times 1 plus, and I'm going to get sneaky here. I'm going to do R over F inside. So 0.07 divided by 2 to the power of 20. Which is let's use this one, clear all. 0.07 divided by 2 is 0.035. Okay. And I have 500 times 1 plus 0.035 to the power of 20 compoundings. Right, so same thing again. And like I said, wow, Emily, that was a lot of work for not that much reward using the calculator, right? And so here, the future value is, oh, maybe I'll put it up here. 994.89, right? Which is the same 994.89,443, which is the same value that we found earlier, right? So however you want to do these calculations is fine. Using the calculator doesn't really pay off until chapter 6, but I wanted to introduce it here. You're more than welcome to use the calculator if you prefer, right? And so, right, notice using the calculator functions. Functions for these types of problems, is not super helpful, right? They're usually the same amount of time, is not I want to say is not significantly faster. But it is good practice for chapter 6, where it will be significantly faster. Where it will be significantly faster. Okay. So, let's do another example. I've got example 189. And I have just enough time to do it here. Paste. So we're going to use the calculator to do this. So determine the number of compounding periods that it takes for an investment of $10,000 to reach $12,000 if money earns a rate of interest of 5% per year compounded monthly. Okay. So a couple of things here, right? I have the present value is 10,000. The future value is 12,000. Which means, okay, we're not solving for either of those. Oops. R is 0.05, although for the calculator, right, we're just going to use 5. But compounded monthly means that the frequency is 12. And we want to find, we want to solve for N. So we can draw this out on a timeline if we want to. There's not a lot going on though today, and some amount of time. 10,000 is going to grow into 12,000. And it's going to take some amount of time to do it, and I is R over F, which is 0.05 divided by 12. I'm not going to solve it though, because I'm going to use the calculator, but you would need it if you were solving it by hand, right? So again, I'm just going to use this list. I just rewrite the list all over again. It's not that bad. So N and interest per year, present value, the PMT, and then I'm going to go over here, the future value, the payments per year, and the compoundings per year. Now I want to solve for N, right? So I'm going to enter 0 initially, and then I'm going to go back and compute it. But the interest per year is 5. Remember, right? The full percentage value. The present value is $10,000. Now, I'm investing $10,000. So I want to get in the habit of, okay, $10,000 leaves my hands. And so I'm going to make that negative. Oops. And then the future value is going to come back to me and I can hold it, right? And it's going to be the 12,000, kind of skipping ahead here. The PMT we're not using, so I'm going to enter 0. I've already entered 0, so until I change it, it's going to stay 0. So I might skip it, might not. And the payments per year has to match the compoundings per year, which is 12. So 12 and 12. So let's see these side by side again. All right. So n I'm solving for, and I know I'm over time, but just got to finish this. So n is 0, 5 is the interest per year, 10,000 negative is the present value, 0 for the payment amount, 12,000 positive is the future value. Then the payments per year, I'm going to change to 12, enter, scroll down, make sure the compoundings per year is also 12, which it is. Second, quit, compute. And I know that was fast, but n is 43.8482712. Okay, which means that technically I would need 44 compoundings, right? Full compoundings. But that's where we'll end today. I'll pick it up on Wednesday. If you have any questions, let me know, and I'll have a look at that initial question before I go here, but it might be an email thing. All right. See you Wednesday. Stop this.